In this video, we'll discuss radicals and rational exponents. Now, a radical is written as the nth root of a, where n represents the index of the radical and a represents the radicand. And that can be a number, a variable, or some expression of numbers and variables combined inside the radical. Now, a couple things are important to remember. First, if there is no specific index stated, that represents the square root, which is an index of 2. That's one of our most common radicals that we deal with, especially in middle school and high school. Also, it is important to recognize that the nth root of a equals some value if and only if the a equals b raised to the nth power. Now that may sound kind of weird, and what is that getting at? There's one specific case that's very important to remember, which is that if my index is even, but my radicand is negative, that creates an undefined solution. And when you use your calculator, it'll even come up as saying undefined or error on the calculator. So let's look at some relationships that are important to recognize. First, if I have my radicand has an exponent and my radical has an index, I can rewrite that as a fractional exponent and say that a raised to the m, if that's in the nth root, could be rewritten as a raised to the m divided by n. And that's true as long as this radical does exist, i.e. what we just talked about. Also, I could pull that index or that exponent off of my radicand and say I'm going to take my whole nth root and raise it to the mth power. And that can be helpful depending on the simplification process. Sometimes it may be easier to take the root and then raise it to the exponent. So let's look at an example. Say we have 8 raised to the 2/3 and we want to write it in radical form as well as simplify. Well, the first thing, let's change that to radical form. Again, we recognize that the 2 in this case is my exponent on my radicand, and the 3 becomes the index of the radical. So this would be the 3rd root of 8 squared. Now, I can simplify this many different ways. Let's look at 3 of those. First, I could go on and just say that 8 squared is 64. And then, okay, let's take the 3rd root of 64. So I need a grouping of numbers. 3 groupings will allow me to pull outside the radical. So I could say, let's just break this down. We got 4 times 16, and I can break 16 down to 4 times 4. So now I've got a group of 3/4, that's 4 cubed, and I've got the cube root, or the 3rd root of 4 cubed will give me 4. A second option, maybe instead I say I want to take that exponent off of my 8, and I want to take my radical and square it. Well, the cube root of 8, I can break 8 into 2 times 2 times 2. So the cube root of 2 cubed is 2, and 2 squared is 4. The third option, I could see what my calculator does. So here's one calculator that can be helpful if you don't have your own scientific or graphic calculator. The Desmos one is a great one. So this is what it looks like on Desmos. The first thing I'd want to do is I'd want to hit this button here that has the nth root. Then I see that I get boxes, and I can click on the box and put my number. So I'm going to put my index of 3. Then I'm going to click on the larger box, and I can do 8. And if I use the caret key, that'll give me my squared. And you see automatically it shoots out my answer of 4. Now there is an important thing to recognize when you're dealing with numbers. If you do this simplification on the calculator and it shoots out some long decimal number, you're going to have to find a different way to simplify, because most commonly, as you're simplifying rational exponents and radicals, the answer should include integers versus decimals. And we'll look at that here in just a second. So let's look at some other rules that can be very helpful with that idea of simplification, especially if we want to keep integers at all aspects. So say we've got these 2 different radicals, and they have the same index on their radical. Now first, I know that a raised to the n in the nth root will equal just the radican. Because if I look at that as a fraction, this is my exponent divided by my index, and anything divided by itself is 1. So it's a to the first. So if I had the fifth root of 7 to the fifth, that's really 7 raised to the 5 over 5, or 7. So that's one of the reasons why we're always looking for, when we're trying to pull numbers out of the radical, it has to have the same index, or same exponent as the index. Another thing that's really nice, if I have two numbers being multiplied, or two expressions being multiplied inside a radical, I can always split them into separate radicals. And vice versa. If they're in separate radicals with the same index, I can combine them back into one individual radical. So let's say I had the cube root of 18x to the 7th. That could be split apart as the cube root of 18 and the cube root of x to the 7th, which allows me then to simplify the cube root of 18 and simplify the cube root of x to the 7th. Vice versa, what if I had the fourth root of 3r squared times the fourth root of 12r to the 9th? I could combine them back together with all those terms being multiplied inside the radical because they have the same index. And this allows me then to say, okay, I can multiply 3 times 12, that gives me 36, and I can combine my exponents because it's the same base, so 2 plus 9 gives me r to the 11th. And the final rule goes back to what we've said before. If I can do my rule with a radical as multiplication, the same can be true with division as long as my b value does not equal 0, because I cannot have 0 in a denominator. So, say I had the cube root of 216 over x to the 12th. I can actually simplify the cube root of 216 divided by the cube root of x to the 12th. That can be simplified. In this form, I can't do much with it. Same here. Here I have the square root of 24x cubed divided by the square root of 2x to the 9th. I see that I've got parts in both of those that could simplify, so the first thing I would do is combine them and then work on simplification. That would become 24x cubed over 2x to the 9th, and we've talked previously that this can be simplified, so that 24 divided by 2 is 12, and then 9 minus 3 gives me x to the 6th in my denominator. Then I can go from there to simplify. So I keep talking about this idea of simplifying radicals. There's a couple of things that can help us as we're doing this simplification. First, we're going to use those 3 radical rules we just talked about to combine or split radicals for simplification. Sometimes I have to combine them and then split them again, or split them and then combine them again. It just depends on what's the easiest process for what I'm trying to do. Next, if I want to pull out a number or fraction from the radical, it has to have an exponential grouping that matches the index. So like I'd said before, if my index was 3, I'd have to have like x cubed or x to the 6th, something that's divisible by that index. And finally, if I have a radical or rational exponent in my denominator, that can't be left for final simplification. Instead, I'm going to have to multiply the numerator and denominator by an expression that will simplify the radical, or that radicand, to have an exponent of 1. And we'll look at an example to help make this make more sense. Let's start with the square root of x to the 5th divided by 6. Now, I can't really deal with them as it is, so I'm going to separate them and look at the square root of x to the 5th divided by the square root of 6. Now, x to the 5th, I'd want to split that because I have this index of 2. 5 is not divisible by 2. But I could split that into x to the 4th times x, because 4 is divisible by 2. And 6, there's nothing I can do with the square root of 6, so I just need to leave it as it is. So now I can say, okay, let's simplify x to the 4th inside the square root. Well, 4 divided by 2 gives me x squared that's no longer in my radical. But the x has to stay in the radical because it can't simplify out, just like I can't simplify out the square root of 6. However, like this last rule says, I can't leave a radical in my denominator. So I have to say, how can I simplify this so that my denominator becomes, in this case, a whole number? Well, what I could say is I can multiply it by itself in this case, because I want that index of 2. I want to make a perfect square inside the denominator. So if I multiply my denominator by the square root of 6, I also need to multiply my numerator by the square root of 6, so that really I'm not changing the value of the expression, I'm just rearranging the numbers. Because the square root of 6 divided by the square root of 6 is 1. So, since they have the same index, I can combine them into a single radical. And here, the square root of 6 times the square root of 6 will give me the square root of 36. And that would simplify to x squared, the square root of 6x, divided by 6. So, yes, this is a correct answer, but this is the most simplified answer. Let's look at one more example. Say that I have the cube root of 112 divided by x to the 13th. A little bit more complex here. First thing I would do is split my radical so that I have the cube root of 112 and the cube root of x to the 13th. Now 112 is a kind of challenging number, and I know that I need to create an exponent of 3 on the number. So I'm going to split it down to all of its simplest forms. It's the easiest way to go in this case, and that would give me 2 times 2 times 2 times 2 times 7. Those are all prime numbers, so I can't split them anymore. In the denominator, I'd say, well, 13 is not divisible by 3, but 12 is. So I can split this back into x to the 12th times x to the 1st. Now let's revise this and say this is really 2 cubed times 2 times 7. And why would I want the 2 cubed? Because now I can say 3 divided by 3 will give me 2 to the 1st on the outside of my radical. And then x to the 12th, and that 12 divided by 3 will give me x to the 4th on the outside of my radical. But I still have stuff inside. My numerator, that's fine to have the cube root of 14, because that's just combining the 2 and the 7. And in my denominator, though, I have the cube root of x to the 1st. And there's my problem. This is a correct answer, but it's not the most simplified. So I have to say, how can I get an exponent of a 3 on x inside there? Well, if I'm at 1, x to the 1st times x to the blank gives me x to the 3rd. If you remember from previous videos, we talked that when I multiply the base by itself, those exponents add together. So 1 plus 2 will give me the 3rd. So I need to multiply both my numerator and denominator by the 3rd root of x squared. And sometimes if you deal with them as fractions, it might be a little bit easier to think about, because this would be x to the 1/3, and this would be x to the 2/3. 1/3 plus 2/3 would give me 1 whole. So now I'm going to combine my terms. So I have 2, the cube root of 14x squared in my numerator, and x to the 4th, the cube root of x cubed in my denominator, which again, the cube root of x cubed will simplify to x. So x to the 4th times x, my last thing I need to do here is just simplify this. And my final solution then would be 2, the cube root of 14x squared divided by x to the 5th.